Welcome to this explainer. Today, we're doing something a little different. We're tearing down that abstract digital cloud and getting right down to the ground floor of networking. We're going to journey beyond your screen to understand exactly how your clicks transform into physical reality. Basically, we're talking about the tangible, physical backbone of the internet that makes all our digital lives possible.
All right, let's anchor ourselves with the classic OSI model. Now, if you've studied networking at all, you've probably spent a lot of time hanging out in those upper layers. But today, we're skipping the application cloud and zooming all the way down to the absolute bottom, the physical layer. This is where the magic really happens, because it's the exact point where software literally becomes physics, and your abstract digital bits turn into electricity, light, or radio waves. Since networking is highly systemic, here's our quick roadmap for today. We'll look at the physical connection, speaking the language, bandwidth versus throughput, copper, light, and air, and finally, beating network interference.
So, Section 1, the physical connection, or where the cloud meets the ground.
Before any communication can actually happen, you absolutely need a physical connection. This is where your network interface card, or NIC, steps in to bridge your device to the local network. And it does this in one of two ways. You can use a wired connection with a traditional RJ45 cable plugged right into your device, or you can use a wireless local area network setup, where a WLAN NIC uses radio waves to talk to a router. Both are physical connections, even if you can't actually see those radio waves. Now, unlike the software side of networking, like TCP/IP, which is governed by the IETF, the physical layer is hard engineering. Because we're dealing with actual hardware, physical cables, and radio frequencies, it's governed by incredibly strict rules from specific regulatory bodies. Organizations like the IEEE and ISO ensure that a cable made in one country is going to seamlessly communicate with a router built in another. It's all about ensuring absolutely flawless interoperability.
Moving right along to Section 2, speaking the language, turning data into signals.
Here's where it gets really cool. The physical layer takes a complete frame from the data link layer and literally shapeshifts it. Depending on the medium carrying it, your data physically turns into one of three things: jagged electrical pulses running across a copper cable, smooth pulses of light shooting through fiber optics, or oscillating microwave signals for wireless connections.
To make that happen, we use something called encoding. Basically, physical layer standards define exactly what a 1 and a 0 look like as a signal. You'll often see a transition, a literal step up or down in voltage, right in the middle of a bit period. This tells the receiving computer exactly what bit is coming through and keeps the whole system perfectly synced up.
And when we go wireless, things get even more dynamic with a process called modulation. This is the fascinating process of taking a carrier wave and tweaking it to hide our digital signal inside. We can change the wave's height, that's amplitude modulation, or AM, or we can change its frequency, which is how close the waves are to each other, and that's frequency modulation, or FM. That's exactly how your Wi-Fi invisibly carries a streaming movie right through the air. All right, Section 3, bandwidth versus throughput, the speed illusion. We've all stared at that internet speed test style, right? Well, prepare for a reality check. Bits don't actually travel faster on a better connection. Seriously? On a standard copper cable, whether you have a 10 megabit per second connection or a 100 megabit per second connection, those bits always travel at the exact same speed, the speed of electricity. So if they aren't moving faster, what on earth are you paying for? Well, you're paying for bandwidth. Think of bandwidth as the absolute width of a highway. It's the theoretical maximum capacity of that medium. It's not about the velocity of the cars. It's about the absolute maximum number of cars that could theoretically fit side by side on that road in a single second. But theory is different from reality, you know? That's where throughput comes in. Throughput is the actual rush hour traffic, the real-world measure of bits making it across the media over time. And this is usually lower than your bandwidth because of network congestion and latency. And then we have goodput. If throughput is all the traffic on the road, goodput is the final number of people who actually made it to work on time. It's your throughput minus all the necessary overhead, like establishing sessions and data encapsulation. Goodput is the actual usable data you get. Let's look at the roads themselves in Section 4, copper, light, and air, the transmission media. Network media basically falls into two major categories. First, we have guided media. This means physical cables like twisted pair, coax, or fiber optics that literally guide the signal down a confined pipe to its destination. Second, we have unguided media, which uses free space for wireless transmission, broadcasting signals out in multiple directions all at once. Now, copper media is incredibly common for sure, but it suffers from attenuation. That means the longer the electrical signal travels, the more it deteriorates, which forces some pretty strict distance limitations. Enter fiber optics. These single-mode and multi-mode patch cords use pulses of light instead of electricity. Because they use light, they can transmit massive amounts of data over incredibly long distances without that same signal degradation. It's exactly why they're the absolute backbone of our global internet infrastructure. Which brings us to our final section, Section 5, Beating Network Interference, the Physics of Degradation. The physical world is messy. Electromagnetic interference, or EMI, and radio frequency interference are the absolute enemies of copper cabling. A beautifully clean digital signal can be completely distorted by outside interference as it travels. This physical corruption is exactly why your internet might randomly drop or lag. Ambient magnetic fields in your home or office might actually change the physical voltage on the wire, causing the receiving computer to accidentally read a 1 as a 0. But outside EMI isn't the only bad guy. Cables also have to fight crosstalk. Crosstalk is what happens when the magnetic field from one wire bleeds into the wire right next to it, inside the exact same cable. To solve this, early network engineers asked an ingenious question. What if we just twist the wires together? And that's exactly why standard network cables look the way they do. With unshielded twisted pair, or UTP, twisting those opposing wire pairs together forces their magnetic fields to literally cancel each other out, completely destroying the crosstalk. Now, for environments with really heavy outside interference, you'd use shielded twisted pair, or STP, which adds a layer of metallic foil or braid to physically block outside EMI from ever reaching the wires inside. We also use coaxial cables in some scenarios. Coax wraps a central copper conductor in flexible plastic insulation and surrounds that with a woven copper braid. That outer braid is super clever. It acts as both this second wire to complete the circuit and as a protective shield against interference for the inner wire. While twisted pair has mostly replaced it for Ethernet, coax is still a go-to today for attaching antennas to wireless devices. So all of these cables, network cards, and wireless access points, they make up what we call our physical topology. That's the literal physical map of where the wires are plugged in and where the hardware actually sits in a room. But remember, this is an entirely different beast from the logical topology, which is the virtual IP map your data actually thinks it's following based on software addressing. They're two halves of the exact same incredible machine. Which leaves us with a fascinating thought to wrap up this explainer. We've seen how bits are boxed in by the actual physics of electricity, light, and radio waves. But as our encoding gets smarter and our software demands faster logical connections, we're rapidly approaching the absolute theoretical maximums of our current physical materials. So how much faster can the invisible physical layer actually get before we need to invent entirely new physical mediums? It's definitely something to chew on the next time you plug in a standard network cable. Thanks for hanging out with me on this deep dive into the physical layer. Keep exploring, and I'll catch you in the next explainer.